this is the second part of our discussion on complex exponents. So far, we have defined what are complex exponents. So in other words, if we want to calculate z raised to power c, where z is a complex number as well as c is a complex number, how do we calculate it? So we define this using the definitions of exponential functions and logarithmic function. So as you can see on the screen that z raised to power c is equal to exponential of c log z, and of course we know that this log of z is a multi-valued function. So eventually z raised to power c is basically a multi-valued function. So we can define its principal value in the following way by using the principal value of the logarithm of z. Okay, so that's what we have done so far. Now we want to focus on particular cases. So for example, if we are calculating z raised to power c and c happens to be a rational number, then what are its relations with our previously known examples? Okay, so for example, is it related to if we are calculating z square, because c can be easily 2. Similarly, if c is equal to 1 by 2, then is it really compatible, or is it really the same definition that we have done so far of z raised to power 1 by 2? And similarly, other rational powers. And of course, we will also try to see that what happens if c is not a rational number. Okay, now let's begin with the case when c is a rational number. So what happens in this case? So according to the definition, z raised to power j over k, we know that every rational number is of the form j over k, where j and k are rational numbers, and of course k is not equal to 0. So according to the definition, this becomes exponential of j over k log of z. Okay, and this implies, since z is equal to r e raised to power iota theta, this implies that this is equal to exponential of j over k log of r e raised to power iota theta, and this is going to be equal to exponential of j over k log of r, because r is the modulus, and iota theta plus 2n pi. Okay, so very simple. And from here we can use the properties of log of real numbers, because r is a real number and j over k are also real numbers. So this implies this is equal to natural log of r raised to power j over k, and then multiplying j over k with this term, we get iota theta plus 2n pi j over k. Okay, so and moving on, we can use the properties of exponential, and this implies that this plus this. Okay, so this implies this is going to be equal to exponential of this log of r raised to power j over k and exponential of this number. Okay, so this is just the simple property of exponents that we have so far, that e raised to power x plus iota y is going to be equal to e raised to power x and e raised to power iota y. So using this we get this expression. And moving on, we can just use the definition of e raised to power iota y. Okay, so e raised to power iota y is going to be equal to cos y plus iota sin y. Okay, and this is a real number, so that's why we can say that this is basically the Euler formula. Okay, so using Euler formula we get this expression, and of course this is the real case, and e raised to power log of r raised to power j over k, and e and log will cancel out each other, they are inverses of each other, and we get r raised to power j over k. So we get this expression. So hence we have the following expression. Okay, now in this case you can see that when we vary n, then it will be giving us different values, but then since cosine and sine are periodic with period 2 pi, so that's why after k values there will be some repetitions. So we can say that the k distinct values of z raised to power j over k are going to be equal to when n is equal to 0, 1, 2 up to k minus 1. Okay, of course in this expression j and k are fixed, but we are trying to find out is this a single valued output z raised to power j over k, is it a single value or many values? and the answer is it is not going to be a single value, it is going to be k values. Okay, and after taking values of n after, okay, so if we take k or k plus 1, so it is going to be the same as the value of z raised to power j over k for these values. Okay, so it is basically a 1 to k function. Okay, and this k is over here. Okay, so that's how we calculate z raised to power j over k. Now let's consider some particular cases. So for example, if j is equal to mk, so what happens if j is equal to m over k? So over here, so z raised to power j over k is equal to z raised to power mk over k. So k and k will cancel out each other, and we will be get z raised to power m. So in other words, we are trying to find out how do we take the power of a complex number, and of course we will observe that is it the same definition that we have done so far. Okay, now let's try to find it out. So z raised to power m becomes r raised to power m, of course. This is over here, and when j is equal to mk, then once again this k and k will cancel out each other. Okay, and similarly this k and k will cancel out each other, and what do we get? So we get cosine of theta plus 2 n pi into m, and similarly the same angle over here. Now as we know that cosine and sine are basically periodic functions of period 2 pi, so we can write down this expression in the following way: cosine of m theta plus 2 n m pi plus iota sine of m theta plus 2 n m pi. And so we can just ignore this term because sine and cosine are periodic with period 2 pi. So what do we get? So z raised to power m is going to be equal to r raised to power m cosine of m theta plus iota sine m theta, and this is of course a single valued function. If we consider this as z raised to power m as a function of z, then for fixed m, of course, this is going to be a single valued function, and the definition is exactly the same that we have done in our previous discussion. So that's one particular case when j is equal to mk. Now let's focus on the next particular case when j is equal to 1. Now in this case, when we take j is equal to 1, then this becomes 1 and this becomes 1. So what do we get? So we get r raised to power 1 over k and cosine theta over k plus 2 n pi over k plus iota sine theta over k plus 2 n pi over k. Now over here we can see that using the fact that cosine and sine have period 2 pi, we can see that when we vary n, then by taking 0, 1, 2 up to so on, all of these are distinct values, but due to the periods of sine and cosine, we will start getting repetitions when n is equal to k and k plus 1 and up to so on. So the distinct values of z raised to power 1 over k can be obtained by taking the values of n to be this. Okay, so we can say that, so hence we get the following expression, and the distinct values of z raised to power j over k, and of course in this case j is equal to 1, so they can be calculated by taking the values of n to be 0, 1, 2 up to k minus 1. Now if we consider the following function, f of z is equal to z raised to power 1 over k, then for each input z, the outputs are going to be k. So it is basically once again a multi-valued function with k outputs, and of course this is compatible with our calculations when we calculated the kth roots of any complex number. Now let's try to focus on the case when c is not a rational number. Okay, now in this case the outputs are going to be infinitely many. Okay, so when c is a rational number, as we have seen that if c is, for example, a power, an integer, for example m, then the output is one single value, and if c is basically some 1 over k type number, where k is an integer, then there are going to be k outputs. But if c is not a rational number, then there are going to be infinitely many outputs. Now let's have a look at why and how this happens. Now let's consider this particular example where we are trying to calculate 2 raised to power 1 over n plus iota over 50. Okay, so in this case, this is the power, and the base is basically 2. So according to the definition, this is equal to exponential of 1 over 9 plus iota over 50 log of 2. Okay, so by expanding log of 2, so this becomes natural log of 2 plus iota 2 and pi, because 2 is basically a real number, so the principal argument of this is 0. So what do we get? Log of 2 plus iota 2 and pi. So moving on, if we just multiply these two complex numbers and separating their real and imaginary parts, we get the following complex number. Okay, and if we use the definition and the properties of exponential function, then we can easily write them down in the following way. So exponential of log of 2 over 9, exponential of minus n pi over 25, and exponential of this complex number. And once again, this log and this exponential, they will cancel out each other, and what do we get at the end? So at the end we get 2 raised to power 1 over 9 e raised to power minus n pi over 25, and once again using the Euler's formula, we get the following expression. Okay, so what do we get? Now the point is, this iota 59, 2, so these are all constants, but there is one number which is varying. It is this number n, and when we vary the values of n, then we will be getting many outputs. So for each value of n, we get one output. So in other words, we can say that there are going to be infinitely many outputs for each value of n. Okay, now if we plot these outputs on the complex plane, then we get the following output. Okay, and now you can easily see that there is a pattern in the outputs of values of this power. Now of course, why this happens? Because you can see that if we consider the output as a complex number with this modulus, and this expression contained information about the argument, then as n varies, because this modulus of this complex number, this output, involves n, and when we vary the values of n, then the modulus is changing. Okay, and of course when n is, for example, minus 100, then they will minus and minus will cancel out each other, and it will be very high number. And if n is 100, then this is going to be minus 100 pi over 25, and it is going to be a very small number. Okay, so as you vary the values of n, you are moving in a spiral, because as n varies, you are either increasing its distance from the origin or decreasing its distance from the origin. So that's the output, and these are going to be infinitely many numbers. So this complex exponent is basically 1 to infinite kind of function. Okay, so for example, if we define the function f of z to be z raised to power 1 over 9 plus iota over 50, then this function is basically 1 to infinite function. In the next discussion, we are going to focus on the rules of exponents. Okay, so there are many rules when we use exponents in real analysis. Then we used many rules, and of course these rules help us in simplifying the calculations, and now we will see that whether these rules also hold in the complex case. So for example, if 1 over z raised to power c is equal to z raised to power minus c, if z raised to power c multiplied by z raised to power d is equal to z raised to power c plus d, and up to so on. Now let's begin with this discussion. So in the first case, we want to see if 1 over z raised to power c is equal to z raised to power minus c. Okay, now this thing holds due to the properties of exponential function, because the reason is when we define the complex exponent, then they involve the exponential function and the logarithm function. So in the very first point of contact is basically the exponential function. So most of the properties hold and not hold due to that exponential function. Now let's see why and how the properties of exponential functions gives us the properties of complex exponents. Okay, now this holds due to the very simple reason, because 1 over z raised to power c is equal to 1 over exponent of c log of z, and since this is once again e raised to power some number, so we can say that this is going to be equal to e raised to power minus c log of z, and of course this is the same as z raised to power minus c. So as we have seen that by using the properties of exponential function, we can easily deduce the properties of the complex exponent. And moving on to the next property, on the same lines, we can prove that z raised to power c into z raised to power d is going to be equal to z raised to power c plus d. And let me state again that we are using the definition, and our first point of contact is with the definition of exponential function. And due to that fact, and due to the properties of the exponential function, we can easily prove this thing. And moving on to the next property, z raised to power c over z raised to power d is equal to z raised to power c minus d. Once again on the same lines, can be easily proved. Now moving on to the next property, z raised to power c raised to power n is equal to z raised to power nc or not. Now this holds only if n is an integer, and it does not hold if n is not an integer. Now to see this thing, we will in a short while we will see an example why this thing does not hold in general. Okay, so the following case does not hold if n is not an integer. Now let's have a look at this example. So we have two powers. So we have iota raised to power 2 raised to power iota, and we have iota raised to power 2 iota. Okay, now the point is iota square raised to power iota can be written as minus 1 raised to power iota, and this is going to be equal to exponential of iota and log of minus 1. Okay, now we can write it down in the following way: exponential of iota. Now log of minus 1 becomes log of 1, okay, and plus iota. Now the argument of this is pi, so we can write it down as pi plus 2n pi. Okay, so this is by using the definition of log, and this is going to be equal to exponent of iota. Now log of 1 is 0, so this becomes iota pi plus 2n pi. Okay, so iota and iota, they will become minus 1, so this is equal to exponent of minus, if we just take common this pi, so it becomes 1 plus 2n. Okay, now let's calculate iota raised to power 2i. So this is going to be equal to exponent of 2i and log of iota. Now we can calculate the log of iota in the following way. Once again, natural log of 1, because the modulus is 1, so plus iota, and in this case the principal argument is pi by 2 plus 2n pi. So in this case we get the following expression. So 2 and log of 1 is 0, and iota will cancel out with each other. I mean, they become minus 1. So minus 2 into pi by 2 plus 2n pi. So this is going to be equal to exponent of minus. Okay, so we can take out this pi, and we can multiply this 2, and what do we get? 1. Okay, plus 4n pi. Now as we can see that iota raised to power 2 raised to power iota is not equal to iota raised to power 2 iota. Okay, so these are different answers. So that's why in general this property does not hold. Now let's have a look if the following property also holds in the case of complex exponents. So for example, if z1 z2 raised to power c is equal to z1 raised to power c multiplied by z2 raised to power c. Now unfortunately this does not hold in general. So if we take z1 to be 1 plus iota, z2 to be 1 minus iota, z3 to be minus 1 minus iota, then if we calculate z1 z2 raised to power iota, then it is equal to z1 iota into z2 iota. But I'm leaving this as an exercise for you, but we can easily see that if we calculate z2 z3 raised to power iota, then this is going to be equal to e raised to power minus 2 pi z2 raised to power iota z3 raised to power iota. So it does not hold in general. Of course, in some cases it holds and in some cases it does not hold. So we can say that in general this property does not hold. Now in this module, we further explored the properties of the complex exponents. So in particular, we saw that which of the properties from real analysis holds in the case of complex exponents. We will continue our discussion in the next module.